welcome to the deep dive.
Oh.
Okay, let's get into it. We've all seen these large reasoning models, LLMs, do some pretty amazing things, right? Especially, those long chain of thought answers where it looks like they're really thinking step by step.
Absolutely. It's quite impressive to watch.
But there's this sort of catch. A lot of the really advanced stuff, like self-correction or figuring something out on the fly, it just kind of pops up. These unpredictable aha moments.
And while those moments are fascinating, showing there's real reasoning potential under the hood, you can't really rely on them.
Exactly. If it's unpredictable, it's hard to scale, hard to trust for anything serious.
Right. Which leads to the big question. Can we actually engineer this? Can we move beyond just hoping for those aha moments and build models with consistent reasoning skills?
And that is precisely our mission for this deep dive. We're looking at a really interesting paper, Beyond Aha, towards systematic meta-abilities alignment in large reasoning models. It's proposing a way to, systematically teach these models core reasoning skills.
Yeah, a structured approach.
So for you listening, this is about getting a handle on how we might unlock more dependable, more powerful AI reasoning. It's kind of a shortcut to the cutting edge here.
Definitely.
So how do we get beyond just waiting for those flashes of insight? The paper lays out this very structured method, explicitly aligning LLMs with three domain general reasoning meta abilities. Can you sort of walk us through what these are?
Sure. So the core idea here, and it's quite foundational, draws from classical logic, specifically Peirce's inference triad, deduction, induction, and abduction.
Okay, Peirce's triad.
Yeah. Think of them together as forming a complete loop, almost like the scientific method. You generate ideas, you test them, you revise them. It gives a solid and, importantly, an interpretable foundation.
So, like the building blocks of thinking.
Exactly. First, you have deduction. This is your classic logic. If you have a general rule, say all humans are mortal, and a specific case, Socrates is human, you can deduce the outcome. Socrates is mortal. It's about rigorous prediction and checking things.
Makes sense. Straightforward logic.
Then there's induction. This is more about spotting patterns. If you see the sun rise every single day, you induce a general rule. The sun rises daily. It's about extracting rules from lots of specific examples, finding patterns, generalizing.
Okay, finding the rule from the data.
Right. And finally, abduction. This one's a bit more creative. It's about finding the best explanation for something surprising. If the ground is wet, observation, and the best explanation is usually rain, rule, you abduce that it probably rained, hypothesis. Think of a detective figuring out the most likely culprit.
So inference to the best explanation. Deduction, induction, abduction.
Yeah.
That framework makes a lot of sense conceptually. But, okay, how do you actually train a model to learn these? It seems like you'd need very specific kinds of practice problems.
You're absolutely right. And this is where their approach gets really practical. They didn't just use existing data sets. They built a whole new set of tasks, specifically designed for each meta ability.
New tasks.
Yeah. And crucially, these tasks were programmatically generated. That means the computer could create endless examples and automatically check if the model's answer was correct.
Oh, I see. So no need for humans to label everything.
Exactly. Which gets around a huge bottleneck and ensures the model is actually learning the skill, not just memorizing labeled data.
That's a massive efficiency gain right there. Okay, so what do these tasks look like?
So for deduction, they use something like logical satisfiability problems. Basically, does this set of starting statements logically lead to this conclusion? It forces the model through that whole cycle. Hypothesize, check consequences, find contradictions, refine.
Okay, rigorous checking.
For induction, it was masked sequence completion. Imagine seeing a pattern like 2, 4, 8, 10. The model has to infer the underlying rule, adding 2 to fill in the blank, which is 6. That pushes abstraction and generalization.
Right, figure out the pattern.
And for abduction, they did something cool. An inverse rule graph search. The model sees an outcome and has to trace backwards through a set of possible rules to find the simplest starting point, the minimal explanation. Really pushes that kind of goal-directed hypothesis thinking.
Wow, okay. So specialized tasks, automatic checking, no manual labeling. That's smart. So you've trained these individual specialist skills. How do you get them all into one LRM?
Yeah.
What's the training recipe?
It's a pretty neat 3-stage pipeline. Stage A is what we just talked about. Meta-abilities alignment. They trained separate specialist models, one for deduction, one for induction, one for abduction, using those synthetic tasks.
Okay, 3 separate experts.
And they used a specific reward system. The model got points for getting the answer right, of course, but also just for following the correct reasoning format, even if the final answer was wrong initially, encouraging the right kind of thinking process.
Interesting. Rewarding the structure, too.
Then, stage B, parameter space merging. This is clever. Instead of just mixing all the training data together, which can be messy, they actually blended the models themselves.
Blended the models?
How? They took the learned parameters, the internal settings of the 3 specialist models, and mathematically combined them like averaging, but with specific weights into a single model checkpoint.
So you merge the knowledge directly.
Exactly. It's very efficient, computationally speaking, and it lets the merged model inherit the strengths of all three specialists. They found, for example, that the deduction specialist's parameters had the biggest positive impact when merged.
So deduction was weighted more heavily in the merge.
Yeah, empirically, the weights they found were like 1.0 for deduction, 0.2 for induction, and 0.1 for abduction. Shows their relative contribution in that merge.
Okay, that makes sense. And the final stage?
Stage C, domain-specific reinforcement learning training. So now you take this merged model, which has these foundational reasoning skills built in, and you fine-tune it further on real-world tasks, math problems, coding challenges, science questions, using standard techniques.
So you layer the general skills first, then specialize.
Precisely. The idea is that the meta-ability alignment provides a much better starting point, allowing the model to learn those specific domains more effectively and reach a higher performance level.
It sounds incredibly logical, this whole pipeline.
Yeah.
But the proof is in the pudding, right?
Well,
did it actually work? What did the results show? Did it generalize?
yeah, the results were actually quite strong. Even though Stage A was purely on synthetic tasks, the merged model showed significant gains on totally unseen real-world benchmarks.
Oh, really? Out-of-domain generalization?
Yes. Across 7 different test sets, math, coding, science, they saw consistent improvements. For instance, on a 7 billion parameter model, the average accuracy went up by 2.5% compared to a standard instruction-tuned baseline. On a bigger 32 billion parameter model, the gain was 3.5%.
Okay, noticeable gains. Any specific areas stand out?
Math, actually. The 32B model saw its average math score jump 4.4 absolute percent points, from about 47% to over 51%. That's a solid improvement, showing these abilities really do combine well.
That is significant, especially in math. And what about Stage C? Did starting with the aligned model help the final fine-tuning?
It absolutely did. That meta-aligned starting point consistently allowed the models to reach a higher performance ceiling after the domain-specific tuning. The 32B model, starting from the aligned checkpoint, ended up with a math score 5.4% higher than its counterpart that only got the instruction tuning. It hit 52.3%.
Wow, so the foundation really mattered.
And importantly, this advantage actually got bigger with the larger model. Suggests it's a scalable benefit.
Okay, that's compelling performance-wise. But does it mean the models are truly learning these meta-abilities? Or just getting better test scores? Are they actually exhibiting deduction, induction, abduction more often?
That's a crucial question, getting at the mechanism. And they looked into that. Their analysis showed a measurably higher frequency of the behaviors associated with deduction, induction, and abduction in the aligned model's outputs compared to the baseline.
How much higher?
For deduction, for example, the rate of observable deductive reasoning steps increased by over 5 percentage points.
So it's not just better scores. The models are actually using these reasoning patterns more.
It strongly suggests that, yes. The alignment seems to genuinely shift the model's internal processing, making these advanced reasoning behaviors more likely and more explicit, moving from that unpredictable aha to something more verifiable and consistent.
This really does feel like a potential shift then. We're moving, like the paper says, beyond just hoping for those moments of brilliance,
Right.
towards actually engineering these core reasoning abilities into the models, making them more predictable, more reliable.
Exactly. And when you think about the bigger picture, this kind of modular, verifiable approach has huge implications. It means we could potentially build models with specific, tailored reasoning skills for different tasks.
Tailored reasoning, interesting.
It lays a path towards systems that are more interpretable, more adaptable. Think about safety audits. If you know the model has strong deductive verification skills built in, that increases trust.
Yeah, I can see that.
Or imagine using this in scientific research workflows. An AI that can reliably generate hypotheses through abduction, test them through deduction, and generalize findings through induction, all within a computational environment. That's powerful.
It really points towards AI that's not just, statistically clever, but genuinely more trustworthy and understandable in how it reaches conclusions.
Precisely. Smarter and more reliable.
So for everyone listening, it's really worth thinking about how understanding these fundamental reasoning modes, deduction, induction, abduction, might change how you approach either building or using these advanced AI systems. The future here looks, well, incredibly promising for more dependable AI.